Here's a video on 2.3.1. How can we make that the largest area? But our goal is really using rectangles, again, to multiply. So we're going to really be doing something a little bit different with these rectangles. Always do not lose sight of the fact that rectangles and this multiplying is really just different rectangles in area, okay? So our goal today is to use the generic rectangle, it's called, to represent multiplication of multi-digit numbers. Multi-digit meaning 2, 3, or greater digit numbers. Today we'll only work with 2 by 2 maybe, and we'll get there. So today you'll explore area model for multiplication. You'll use what you know about place values, area, to create the greatest possible product or result of multiplication. As you work with your team, please keep these questions in mind. Where should we place the digits? How can we be sure that we have the greatest product? So, for example, 2 times 3, by the way, are factors, and they create a product of 6, right? That's the result of multiplication. Okay, this link right here is in, will be one of the links that I'll have in the at-home learner support if you'd like to click on that and use that. That is this right here. It'll load up this page where we can take out base 10 blocks. However you need to make that work, okay? So we'll be using that today. We'll be coming back to this one here in a little bit. All right, let's go back here. So the first question says your teacher's going to pick 5 playing cards. I actually just used my phone to pick 5 random numbers from 0 to 9. I don't know why I had 0, but anyway, for you to see here, work with your team so that the digits to create a 3-digit number and a 2-digit number that multiply to give the greatest product. Work with your team to develop a strategy that you can explain to the class. So what it's saying is you're going to take these numbers and then you're going to try to fill this in to make the greatest product. Why don't you pause the video, just try it for a little bit. Don't spend more than 5 minutes on something like this. All right, now that you've given this at least a try, what did you hopefully discover? Hopefully, to get the largest product, you didn't put numbers like 3 or 4 here, and those sorts. So those wouldn't have been good picks, right? Hopefully you found that stuff like the 8s and 9s there are going to give us larger numbers. Now, just because you put the 9 here and the 8 here doesn't mean that it necessarily works, or 8 here and 9 here. What you're going to find is it really could matter what numbers we have down here and stuff like that. All right, so what's the exact answer for that? Actually, it's not really that important. What's more important is that you understand that where we place these numbers in these 5 places in this case can change the multiplication. All right, so let's start talking about some of that. We're still going to worry about this for a brief moment, but I say worry loosely. So Alan and Deborah are trying to decide where to place a 2 and an 8, and the box is shown here. So you can see the 9 box times 1 box. So which one should go in here, the 1 or the 8? Their goal was to make a product as large as possible. Think to yourself, no pencils or calculators, what Deborah should do with the other 2 digits to make the greatest possible product. Then write your ideas on paper and discuss them with your team. So, or just try it once. Think about it in your mind. What would be better? Would it be the 9, 8, or the 1, then 9, 8, or 9, 2, and then the 1, 8, or 1, 2, right? So we can't use them both. You have to use 1, 8 in here or 2 in here, and then the other one has to go in there, okay? Well, what'd you come up with? Well, Alan thought that the 2 should go next to the 9 to make it 92, and the 8 should go next to the 1 to make it 18. He used his base 10 blocks to help him draw the figure to justify this answer. Wow, that's a lot of base 10 blocks. Where in Alan's picture do you see the 2 of the 92? 2 of the 92, huh? Where would that be? Boy, this is really hard to see here. And the 8 of the 18, huh? Well, we have to think about the 9 when we think about that particular 9. The 9 is in the 10s place. Let me try that a little different. The 9 is in the 10s place, and the 2 is in the 1s place. The 8 is also the 8 is in the 10s place, and the I'm sorry, the 1 is in the tens place and the 8 is in the ones place, right? So that matters here because if we take a look here, the side length is 10. Side length is 10, 10, 10, 10. Notice that these are the tens place. And then on the far right here, when you come in here, there is a 1 and a 1. Those are the ones place. Here I have a 10. And then when I go in here, I have a 1, 1, 1, 1, 1, 1, 1, 1. All right, so now when I look at this, what do I see? Right here, I see a length right here of what? 92. I see the two ones right here, and I see 90 in the tens place there. And when we look at the 18, right there, right? That looks like the 18. Okay. What are these ones? Well, that's just filling in those spots, right? All right. What part of the picture represents the product? All right, so we have the 92, and we found out where the 9, 2, and the 8 of here, and then where we found out where that information goes, but what part of the picture represents the product? Well, we have to think back to area of rectangles, right? Area of rectangles is multiplying the length times the width, right? The length times the width. So if we have the length times the width, right? The length times the width, we have what? We have the area inside of this. But if I also take the 92 and multiply it by 18, don't I get the area? I get the area, and I also get what it multiplies to. So the blue part is the area, and it also represents the product. Whoa, that just made it disappear if I put it on there too much, right? It represents the product. So the product of 92 and 18 is the area of the rectangle. That's the most important part that we're connecting to today. Let me just start back up here. Students will use the generic rectangle. That's what we're working on today. Area models to represent multiplication of multi-digit numbers. So generic rectangle area, multiplication, multi-digit numbers. This is the most critical part here to kind of get us put together, okay? So if you recognize that if I have a 92 and an 18, and that area is the multiplication of those, that's the key part. So let's keep moving here. If Alan and Deborah had done the opposite, put the 8 by the 9 to form 98 and the 2 by 2 with the 1 to form 12, would the product area have been larger or smaller? Support your thinking by drawing a figure like Alan's for this new product. Now, did we find the new product? We didn't find it yet. Okay, so pause. Why don't you create your own little rectangle thing? It should look like this. Okay, see the 98 on top and then the 18 on the side on the left. Okay, I'm sorry, the 12 on the left. 98 on top and the 12 on the left. Now, we don't know if that product is bigger or not, right? I think what we should recognize is that it will actually be larger. Okay. Now, if we larger or smaller, take a look up here. What do we have up there? We have 1, 2, 3, 4, 5, 6, 7, 8, 9 100 blocks. So we have 900 up there. This is the 92. 92 times the 18 to equal 900 blocks up there. Now, how many tens blocks? Well, one of these has 8. Plus another 8, another 8, another 8. I think just by looking at this, we can tell that that one, the 92 times 18, is going to have the larger product, right? Now, I don't want to spend a ton of time doing the counting because that's not the most important part about today, okay? So the 92 times 18 is larger. So if I said 92 times 18, going back to our less than, greater than symbols or inequalities, we could say that 92 times 18 is going to be greater than 98 times 12. Okay. Alan's working with the hundreds block, the 5 blocks, and the 6 1 blocks. He wants to use all these blocks to make another rectangle. Obtain blocks from teacher, right? Here we go. Let's take a look. That's what I was talking about right here. There is the 100s block. There's the 5 tens block and the 6 ones block. And what they want to do is he wants it put together to be a rectangle. So I put them all out here right away. If you double tap this, you can move them, right? So if I start placing those tens on there, right? I guess I could do that. I wonder, I don't know, could they go here? Look at that. They're kind of piecing together, aren't they? No, that's not a full rectangle. I wonder if these will fill up, won't they? Let's try that. Whoops. And look at there. There, we've made a rectangle. We could draw that, couldn't we? Right? On the far left side, it looks like I have a length of, well, I have the 10 plus the 2 ones, so the left side would be 12. I can't write on here. And the top looks like it would be 10 plus 3 greens, so that'd be 13. Let's go back to this. Put it as a rectangle. You could do it differently if you want to. Here's multiple rectangles that you could see right there. Okay? So those are some possibilities. Are the dimensions of the rectangle the same, or are some of them different? Well, if we recognize actually, this one has 13, 13, and 13. The other one and the other side length is 12, 12, and 12. It looks like even though the dimensions might switch the spot on there, they are still the same, right? They are still the same. So Alan labeled the dimensions of his rectangle 10 plus 2, and then the other one to 10 plus 3. Why might these labels make sense? 10 plus 2, that represents 12, and that one represents 13. I do see where that could be. Look at this. Here is, like, for example, the middle one. Here is the 10 that we would see right here, and there's the plus 2 right there. Notice how that equals the 12. Here's 10 plus 3. 10 plus 2. 10 plus 3. Let's try this one. This one looks different. Do you think that one still works? There's the 10 plus 1, 2. Here's the 10 plus 1, 2, 3. Still works, doesn't it? So that makes sense to me. Which of the possible arrangement makes it easier to see the dimensions and area of the rectangle? Well, I felt like this one was tougher. Could it be done? You bet. But I felt like one of these made it easier, didn't it? Just a little easier to see the 10 plus 2 and the 10 plus 3. Either way, sketch the rectangle that you choose. It's up to you. I don't care. How are the total values of the blocks and dimensions of the rectangle related? If one block has 1 square unit of area, what is the area of Alan's rectangle? Explain at least 2 ways you can determine the area. Well, if we take a look at, say, this left one right here, right? Let's put all that together. I have one 100 block. Right? Now, what I'm doing is I'm doing this as an area. I'm adding up my area. There's 100 blocks, and then I have 5 of the blue ones, so 5 tens, so plus 50. Plus 6 greens, so 6 greens would be a plus 6, right? My area is 156 square units. Well, let's do the multiplication once. Let's actually do the multiplication. Let's do the factors. I'm going to use that common language, 12 times 13, to get our product, okay? I'll do that on the side here, 13 times 12. 3 times 2 is 6. 6 or 2 times 1. Right? So 3 times 2 and then 2 times 1 to give me 2. Then I'm going to multiply using the 1. So because I'm moving over to this one in the tens place, I need to put a 0 right here. Okay? So 1 times 3 is 3, and 1 times 1 is 1. Add that all up. I have a 6. 2 plus 3 is 5. Plus 1, 156. Notice how the units, or the area, there's the key part, right? The area and that number are the same. We've done 2 ways to determine the area. We've done the multiplication, but we also did the area, and that's the key connection today. Again, that's the key connection. All right, so 54. We're closing in here. I'm sorry, I don't know what happened on that one. So Alan has another idea. This time he's trying to multiply 12 times 13 and get an exact answer without having to build the product with base 10 blocks. Wouldn't you agree that doing it with base 10 blocks or these base 10 blocks is a lot of work? So what he's done is he's come up with a little bit different area. So he has the 10. and 10 plus 2, and he has the 10 plus 3. So I can key in on this. I know it kind of covers part of it up, right? But 10 plus 2, right? And what I'm going to do is I'm going to notice that if this is 2, that is also 2. And then if this one's 3, this one's also 3. Look at it as 4 different rectangles. You know what? I'm going to do this. Whoops, what happened? This one, I have 10. And then I have, let me choose another, that 10, right? So notice that I said 10 times 10, right? The area of that rectangle is 100. Over here to the left, I have, that one's 10, right? So I have 10 times the blue 2 to get me to 20. Now down in the lower left, I have the green 10, right? Because that's 10 also. If that's 10, there's 10. 10 times the red 3 times 3 equals 30. And I have the blue 2 times the red 3 to give me what? 6, right? Notice this whole thing is just 4 rectangles that I'm finding the area of. The rectangle in the upper left is a 10 by 10. The rectangle in the upper right is a 10 by 2 rectangle. The rectangle in the lower left is a 10 by 3. And the rectangle in the lower right is a 2 by 3. Now these aren't drawn to scale, but that doesn't matter. Notice the area of the upper left one is 100. The area in the upper right one is 20. The area in the lower left one is 30. And the area at the bottom one is 6. If we add up all those areas, 100 plus 20 plus 30 plus 6 is 156. Isn't that what we just talked about? I think I jumped the gun on some of these down here. We examined it, discussed with the team how it relates to build the shape. Why did he label the size 10 plus 3 and 10 plus 2? That 10 plus 3 and 10 plus 2, just like this. 10 plus 3, 10 plus 2, right? Actually, I guess we could say it's really this one, right? 10 plus 2 and 10 plus 3. And then let's scroll down here. That what we call this is the generic rectangle. I think I actually was not supposed to find the answer, but I did it already. We are supposed to fill in the other 3, right? So let me do a reminder. This one's 10 times 2 times 10, which is 20. 10 times 3, which is 30. And then 2 times 3, which is 6, right? I kind of jumped up there and did it already. All right. Find the areas of the 4 smaller rectangles, right? How can you find the total area? Oh, I already did that one, right? We added all of these together. 156. Find at least 2 ways to do this. Find the total area. I don't know what our second way would really be with this. I feel like that's a good way for us to do that right now. Alan would like to use the generic rectangle strategy to do more complex multiplication problems. Work with your team to help Alan draw a generic rectangle to multiply 59. I'm going to write these down here, times 46. Okay. So if we think about this generic rectangle is not drawn to scale, but if I look here, that's the 5 in the tens place. So there's my 50. 50 plus that 9. We'll call that a 9. There is, right, the 59. The left side we will call 46, right? But this is the tens place. There's my 40 plus what? My 6. Again, these rectangles are not to size. I know that this is not 40 and 6 in exact size. We're just pretending that those lengths represent that. Excuse me. Now let's multiply. Before we do that, let's do this. There's my 40. This one, that side length is also 40, right? All right. Now, if this is 50, then this one's 50, that length right there. Right, just think about these rectangles and what their lengths are, okay? If this one is 9, then this side length is 9, and we still have one more left, don't we? Let's go with this green. If this is 6, then this side length is 6. Okay, Focus on that rectangle right now, right? What is its length? Its length is 50. What is its width? It's 40. Multiply that. 5 times 4 is 20 with 2 zeros after. That is 2,000. Focus on this rectangle. What is its length? Its length is 40. What is its width? 9. Multiply that out. 4 times 9 is 36. Plus 0. All right, 49 with the 0 at the end. You could always do that on the side. 0, 6, 3. All right, focus on this rectangle. What is its length? 50. What is its width? 6. What is its total? 300. And then let's focus on that rectangle. What is its length? 9. What is its width? 6. What is the total? 54. Right? There it is. There's our rectangle. We are multiplying 59 times 46, but we're using the area model. Now, how do we get the total? We add these all up, okay? 2,000, right? The upper left-hand rectangle plus the upper right-hand, 360, plus the lower left-hand one, 300, plus the lower right-hand one, 54. All right, let's add that up. Of course, at an angle. Nice job, Mr. Crone. 4. 6 plus 5 is 11. Carry the 1. 1 plus 0 plus 3 plus 3. I kind of put that 1 in a bad spot. It looks like it's above the 2, doesn't it? All right, 1 plus 3 plus 3. That's 7 plus 2. Whoops, what happened? I don't know why that disappears at the bottom since we upgraded here. 2,714. Okay. Now, just as a quick check, 59 times 46. Let me just prove it. 59 times 46. Multiply. That's 54. Carry the 5. 6 times 5 is 30. 30 plus 5 is 35. Now, because I move over to this tens place, I got to put a 0 there. So now we're back here. 4 times 9 is 36. I don't need this 5 anymore. We'll carry the 3. 4 times 5 is 20 plus 3, that's 23. Let's add that all up. 4 plus 0, that's 4. 5 plus 6 is 11. 1 plus 3 plus 3, that's 7. 2,714. It's the same. Here we go. So I think that's it. So let's go back to the top. Let's review. Students will use the generic rectangle. We now know what the generic rectangle is to represent multiplication of multi-digit numbers. So, can you use the generic rectangle to multiply multi-digit numbers? That's our goal today. I think we've at least introduced it. If you have any other questions, let me know.